Hello, good evening. We are group 5 and today we are going to present our assignment 2. So let's introduce our group members. Mas Nurliana Diana binti Muhammad Samsudin, Kanisha Dian anak Geliga, myself Priscilla Resi anak Gasan, Nur Naziah Ezari binti Amansa, and Atira Adelia binti Rali. Before we start, here is the table of contents for our presentations. First, we have the objectives and introduction. Next is the methodology we use. Then we will show the results. After that, we will explain the discussions. And lastly, we will end with the conclusion. So let's begin. So let's begin with our introduction. This assignment explores 3 important pulse modulation techniques, which are pulse code modulation (PCM), pulse width modulation (PWM), and delta modulation (DM). So these techniques are widely used in communication and control system to convert analog signal into forms suitable for transmission, for instance, processing or control. PCM digitize analog signals by sampling and encoding them into binary code. PWM represent analog values by varying the width of digital pulse. DM simplifies PCM by encoding only the change between signal samples. So each technique will be analyzed for its advantages, limitations, and suitability in different applications. To demonstrate practical understanding, a small-scale model will be designed using one of the techniques. So let's move on to our objectives. First, to understand and explain the principle and mechanism of pulse code modulation (PCM), pulse width modulation (PWM), and delta modulation. Secondly, to compare and analyze the advantage and disadvantage of these techniques in applications such as telecommunications, audio processing, and data transmission. Lastly, to design, simulate, and evaluate a communication system using a selected modulation technique, focusing on signal quality, data integrity, latency, and bandwidth efficiency.
So next, the methodology. First, the selection. MATLAB was chosen for its powerful signal generation, logic processing, and data visualization capabilities ideal for simulating PWM system. Second, analog signal generation. A 50 Hz sine wave was created and scaled between 0 and 1 to represent a variable speed control signal over a 0.1 second simulation period. Third, PWM signal generation. The sine wave was compared with a 1 kHz triangular waveform to generate a PWM signal. The output was set high when the sine value exceeded the triangle value, forming a digital waveform with varying pulse width. Fourth, signal reconstruction. A second-order Butterworth low-pass filter was designed and applied to the PWM output to reconstruct the original analog signal, simulating how a real DC motor filters high-frequency switching. And last, visualization and analysis. 3 time domain plots were generated: the input analog signal, the PWM waveform, and the filter output. These were analyzed to confer accurate PWM behavior and signal reconstruction.
As you can see, this is the coding DC motor speed control using PWM that we use in the MATLAB for our project. Next, I will explain the simulation results. So these simulation models how a DC motor speed can be controlled using pulse width modulation, and how the analog speed signal can be reconstructed from the PWM signal using a low pass filter. So for plot 1, original analog signal, this plot shows the original analog control signal, which varies sinusoidal. This signal represents our target motor speed over time. So in other words, what the motor should do. And then for plot 2, reconstructed signal, filter PWM. Here we apply a low pass filter to the PWM signal to reconstruct the analog waveform. It closely follows the original control signal. This shows that the PWM technique successfully controls the average motor speed. Now for plot 3 PWM signal 1 bit stream, this is the digital PWM signal sent to the motor. So each pulse width corresponds to the level of the analog signal. At 0.01 seconds, the signal's peak, the pulses are widest. As the analog value drops, so does the pulse width. PWM encodes analog information by changing pulse width. A DC motor or low-pass filter smooths these pulses to create a continuous signal. The reconstructed waveform confirms the effectiveness of PWM for speed control. So in conclusion, PWM allows efficient control of analog values using digital signals. A simple low-pass filter like the inertia of a motor can reconstruct the intended analog behavior. So this simulation visually confirm how PWM drive a motor to follow a varying speed reference.
Next, I will present the discussion of the simulation carried out in MATLAB model the behavior of a PWM-based motor control system. A 50 Hz sine wave scale between 0 and 1 was used as the analog control signal to simulate varying motor speed. This signal was compared against a 1 kHz triangular waveform to generate a PWM output where the width of each pulse corresponded to the instantaneous amplitude of the sine wave. As expected, whether pulse occurred at the sine wave peak and narrower pulses near the zero crossing. To simulate the motor response, the PWM signal was passed through a second-order Butterworth low-pass filter, effectively smoothing it into a waveform that closely followed the original sine input. The resulting pulse showed the analog input, the filter reconstructed signal, and the PWM waveform, confirming accurate signal generation and modulating behavior.
In conclusion, the simulation successfully demonstrates the complete process of PWM generation and signal reconstruction. The results show that PWM is an effective technique for digitally controlling analog behavior, such as the speed of a DC motor. MATLAB played a central role in this simulation by allowing precise waveform generation, logical comparison, digital to analog conversion through filtering, and detailed graphical representation. This type of modeling is valuable not only for academic understanding, but also for designing and verifying real-world motor control system in embedded application. That's all from us. Thank you.